Hello there. We're going to do some problems now from chapter 9. There'll be some practice problems, talk about some issues from chapter 9. So I want you to take notes and think about how to do these problems and send me any questions you have. So the first problem says a scientist is interested in the sleeping patterns of the otters in his county. There are several thousand otters in his county. It is claimed, so we have a claim, it is claimed that 40% of the otters there sleep on land while the rest sleep in water. He decides to test this. He takes a simple random sample of 500 of the otters and finds that 35% of them sleep on the land. So that's 35%. That is our sample statistic. That is our p hat. So I'll call that 0.35. And so it's certainly different from 0.4, 40%, but is it statistically significantly different? So we're asked to perform a test of significance, or otherwise known as a hypothesis test. And so we must do the THAME acronym whenever we do a test, THAME. So the first thing, and I wrote out most of the answer for you. I just want you to fill in the blanks. So the name is a simple thing to answer. The type of inference, and that is, it is a one proportion z-test. With proportions, we do z-tests and make z intervals, and that's a z. All right, so the null hypothesis is just going to be whatever the claim is that p is equal to 40% or 0.4. The alternative is what we suspect might be true. Are we suspecting greater than or less than? It doesn't say up here. And so therefore, this is not equal to. In other words, it's a two-sided test, okay? Now, whenever you do your hypotheses, remember, don't put p hat here. This is p, all right? You have to define p. P is the proportion of all the otters in this county that sleep on land. So that is our parameter, and there you go. And so that's how you do your null hypothesis, alternative hypothesis, defining your parameters. So that's the way you do it. All right, so then we must check our assumptions. We must make sure we're getting good data. Of course, this is otherwise known as checking the conditions, and you have to understand these. This is the third chapter. We've really had these, and understand the why behind each of these. All right, it says a simple random sample was taken. So the first condition is the random condition. It is met. That's always a condition. It's always the most important condition that ensures that we have no bias in our selection techniques. All right. Then we have independence. All right. So there must be at least 5,000. You take your sample size, multiply it by 10. So there must be 5,000 otters. There must be 5,000 otters. All right, in this county for our sample size to be less than or equal to 10% of our population size. So that guarantees independence. We have to do this because we have sampling without replacement. We are not replacing these otters, all right, when we take them out of the population. So we're changing the population a little bit, but we're not changing it significantly as long as the population is big enough. And so this ensures us what? Right. It ensures us that with the formula for the standard error will work. And so then the next thing we have is normality. Well, how do we have normality? Remember, we have n times p and n times 1 minus p greater than or equal to 10. And use your p naught for p. So our sample size is 500. So we will say 500 times 0.4. Don't use the 0.35. Don't use your p hat here. Okay, you do it if you're making an interval, but not for the test. So 500 times 0.4, 500 times 0.6. And so that times that would be 200, that'd be 300. And so they are both clearly bigger than 10. So what is met? Normality is met. Or another way of saying that, the sampling distribution of all possible values of p hat's approximate normal. So there's how you do your assumptions, okay? All right, very good. And so then we have our mechanics. We have to find our test statistic p-value. And so let's find that. So we'll find that. So we will say stat, we will say test, and we go down to option 5. This chapter is all about option 5 and option 6. So one proportion z-test, there's the name of our inference, by the way, the type of inference. So our null hypothesis value is 0.8, so we have 0.8 there. The number of successes, now it doesn't give us that. Don't put 35% or 0.35 there. It's 0.35 times 500, 0.35 times 500. Your X's are your number of successes. It has to be an integer, okay? So it's 175, and our sample size is 500. So we go like that. Our alternative is not equal to, so we hit enter on that, and then we hit enter on calculate, and I did something wrong. I entered the wrong value for P naught, my bad. So let's try it again. Stat test number 5. Yeah, that's 0.4. I don't know why I put 0.8, 0.4. There we go. And then not equal to, and then we do calculate and boom. And that's better. So we do that. And so we get that. So I don't know if that was off the screen, but I'm going to do it again. Stat test, one proportion z-test, and then there's your hypothesized value. There's X, your number of successes, okay, 0.35, which is 0.35 times 500. And so we go like that. And that tells us, there's our z-test statistic, negative 2.282. So this would be negative 2.2822, let's say. And so what is our p-value? It's that. And call it a p-value. Don't call it p, even though it says p there, because p is a population proportion. So it's that. So that would be 0.02248 about. And there we go. There's your mechanics right there. And so then you must draw your conclusion with your p-value, which means we have to decide whether to reject the null or not, and do we have convincing evidence for the alternative. All right. And so we will say this p-value, and you write down what it is, 0.02248, okay, is less than. You want to comment, is it greater than or less than your alpha? And in this case, we were given an alpha, so we use 0.05. So since the p-value is low, we reject the null. We reject, so I reject the null. So thus, there is convincing evidence is the right way of saying it. Convincing evidence that, and then you restate the alternative. P is not equal to 0.4, and then P is defined above. Now, if it wasn't defined above, you'd need to define it here, okay? So P as defined above, okay? So there we go. There we go. So we got convincing evidence that the proportion of all the otters in the county that sleep on the land, we have convincing evidence that it's not equal to 0.4. Now, so that is how you do a hypothesis test right there. That is the heart of the chapter. But there's also other things you need to know, one of which is to interpret the meaning of the p-value. This is drawing a conclusion with your p-value. Understand the difference between drawing conclusion and interpreting. Interpreting the meaning of the p-value means to state it as a conditional probability. And you would say this, assuming the null is true. In other words, assuming that the proportion of otters in this county that sleep on land really is 0.4, the probability of getting a sample portion as unusual as 0.35, because that's what we got for our p-hat, 0.35, or more unusual is what your p-value is, 0.02248, like that. And so that's interpreting your p-value, stating it as a conditional probability. The conditional probability is the probability of getting a sample value this unusual, given that the null is true. And so there we go. All right, so the next thing is this. So the next thing we have to do on the second page is to create a 95% confidence interval with this context and comment on the connection between the interval, the p-value, and the null hypothesis value. Well, let's create a 95% confidence interval. Remember, back in chapter 8, what we would do is we would say, well, they gave us the p-hat is equal to 0.35, and they gave us that the sample size was equal to 500, right? And so we can make a confidence interval with that. And so we will do that with our calculator, 95%. And so we will go stat, test, and go down to option A, the 11th option A right there. So one proportion is the interval. So and notice it went ahead and put the X in the end for, so if it's 175 or 0.35 times 500. And so it's just that. Now we have to change the confidence level to 0.95. And so there's our confidence interval. So our 95% confidence interval is, so 0.30819 to 0.39181. Those are the plausible values for P at this level. And so what is the connection between this interval and, our hypothesized value is equal to 0.4. That's our null hypothesis. Okay. And our P value is low. Our P value is equal to 0.02248, okay, which told us to reject that. Well, this value is not in the interval. And these are the plausible values. So the way you make the connection between these, you would say 0.4 is not inside this interval. So it is not a plausible, value for P at 95% confidence. You really sort of need to mention the 95% confidence. At 95% confidence, and should be rejected at alpha is equal to 0.05. If it's not in the 95% confidence interval in a two-sided test, the p-value is going to be below 5%. These two have to add up to 100%, by the way. If this was 99% confidence interval, it would correspond to an alpha of 0.01. So if it wasn't in the 99% confidence interval, then the p-value would be below 0.01 on a two-sided test. So anyway, and then let's mention the p-value. The low p-value, 0.02248, which is less than 0.05. Okay. Also tells us to reject the null hypothesis of P is equal to 0.4. There you go. So that's that. And so with that p-value, by the way, we would not reject it at 0.01. So we're expecting it to be in the 99% confidence interval. And just for the fun of it, why don't we look at that? So if we go stat, let's make an interval of 99%, stat test, and go down to option A, 1% z interval. Let's just change this to 0.99. And I bet 0.4 is going to be in there. And sure enough, it is. 0.4 is in there. So at this level, we would not reject it. But anyway, I don't want to start rambling too bad. All right, here's the hardest problem maybe we have all year. But I like doing a problem like this because it sort of forces you to understand a number of different things about AP stats. And so therefore, let's do this problem. This problem involves finding the probability of type 1 error, which is insanely easy because it's just equal to alpha. The probability of type 2 error and the power are a bit of a cumbersome calculation. So let's see if we can figure this out. So each day a factory manager receives a truckload of apples to make apple pies. If he has statistically significant evidence at alpha is 0.05 that more than 15% of the apples have flaws, he rejects the entire truckload. He takes a simple random sample of 400 of the apples and finds the proportion that have flaws. What values of the sample proportion would cause him to reject the truckload? Well, what we're going to do here is we're going to test the hypothesis where P is equal to the proportion of flawed apples in a truckload. And we're going to say if it's 0.15, it's okay. So the problem is if it's significantly greater than 0.15, is P is greater than 0.15. So if our P hat is not just bigger than 0.15, but statistically significantly bigger than 0.15, it'll cause us to reject the truckload. Well, if alpha is 0.05, at what value would cause us to reject the truckload? Well, here is our sampling distribution, assuming we've got a good truckload. In other words, 0.15, 15%. All right, our sampling distribution will be centered around that because when we take a sample of size 400, okay, our proportion of flawed apples probably going to be somewhere around 0.15. That's not the best looking normal curve I've ever drawn, but probably going to be somewhere around it at a very approximately normally around it like that. And so it would look like that. So this is if it was a good truckload. Here's all the values of P hat. But this is saying if it's statistically significantly more than 0.15. So how far up here do we have to go before we reject it? That's what the alpha value establishes. Alpha is the percent of the good curve that you're rejecting. And alpha 0.05 means if you're in the upper 5% of the curve, you're going to reject it, okay? The question is, what is this value that is right there? And so in other words, it has 5% of the curve above it, which means 95% are below it, which means this is the 95th percentile. So how can we find the 95th percentile in a normal curve? How can we do that? inverse norm. All right, so we would say inverse norm of 0.95. The mean here is 0.15. And then the standard deviation of our sampling distribution, as we've done for 3 chapters now, is the square root of that times 1 minus that, which would be 0.85 over our sample size of 400. And so this would be our left area. That is our mu, and that is our sigma of our p hats, And let's see what we get. And so we shall say inverse norm. So we go second vars, inverse norm. And so, excuse me there, buddy. So this would be 0.95, and then 0.15 is our mean. Standard deviation, the square root of 0.15 times 0.85 divided by 400 and left area. And so there it is, 0.17936. So 0.1793665. That is our p hat. So anything beyond this, anything above that value right there, about 0.179, about anything greater than that, and we're rejecting the whole truckload. So this is what is known as our rejection region. Any p hat above that value, anything below this, we call this our fail to reject region. So if we get one of these p hats, okay, it causes us to reject it. Now, think about this. What happens if we do get one of these p hats? Let's say this really is the true curve and we got a good truckload, but just by chance, we get one of the p hats that's up here. So we end up rejecting the null when it in fact is true. And what is that? That's type 1 error, okay? Remember, so what I encourage you to do when you're asked about type 1 error is just immediately say the phrase 1 is hot. 1 is hot, immediately say that so you won't get it mixed up. And what that is saying is in type 1 error, the null is true. And it's an error, so I must have rejected it, but I reject the null. And so type 2 error is when the null is false. It's the opposite of that. The null is false, and it's an error, so I failed to reject, but I fail to reject the null, like that. And so then power goes along with type 2 error. Power is a type 2 situation. The null is false. Null is false. Power is the probability I will reject the null. Okay, I'll do the right thing and I'll reject the null. So here, type 1 error, if this is in fact the true distribution, and these are, and we have a good truckload, it could be just by chance we get more than 0.179 in our sample, we reject a good truckload, and that's type 1 error. And by alpha defines the percent of time that's going to happen. So the probability of type 1 error, the probability of type 1 error is always equal to alpha. It's always equal to alpha, and that's 0.05. So that's an easy question. Okay, that's an easy thing. The probability of type 1 is always 0.05. All right, so then it says this. It says, unbeknownst to the manager, a truckload apples comes in, it has 20% flawed apples. Okay, find the probability of type 1 error. I already did that. Probability of type 2 error in the power. So what's happening here is we have another curve. So this is the hypothesized curve, but we have in essence, in this situation, the true curve is centered at 20%. 20% is going to be about right there, maybe. And so the true distribution looks like that. It looks like that, okay? It's centered at 0.2. Okay, so this is a bad truckload. And so when I take a sample from this bad truckload, I'm going to get probably around 0.2. But here's the problem. So if I get a p hat on this part of the curve, it falls in the fail to reject region. And that means I will not reject a bad truckload of apples. And that is what we call type 2 error, failing to reject a bad truckload. Okay. So to find the probability of the type 2 error, it's the overlap. Okay. It's the overlap. So it is this striped area here, this striped area there. So how can I find an area on a normal curve? What calculator function do we have that can tell us the area of a normal curve. That's normal CDF. So I'll do normal CDF right there. So normal CDF right there. So to find this area, I will say normal CDF. We have negative infinity, 2, and this is 0.1793665. The mean of this bad curve is 0.2. And then the standard deviation square root of 0.2 times 0.8 over 400. I like that. Okay. So let's see what that is. And so we shall say second distribution, normal CDF, negative infinity to 0.1793665. That's plenty of sig figs, I think. The mean is 0.2. The standard deviation would be the square root of 0.2 times 0.8 divided by 400, right like that. Here we go, hit paste. And then that is that area. That, in fact, is the probability of type 2 error. Type 2 error is the overlap. Okay, it is the area of the bad curve that overlaps into the fail reject region. See, these p hats over here, okay, they would lead to rejection, and I would reject this bad truckload. And what happens when you reject bad things? That's power. It's like Superman. And it's always equal to 1 minus the probability of type 2 error. Okay, they're a part of the same curve. Okay, so power is equal to 1 minus the probability of type 2 error. And so that is going to equal to 0.8489. And so that is power. Okay, so of course you could have done normal CDF to find that as well. So one of the things is we really like power. We really hate type 2 error. We hate it when we put up with bad things. So the big question that comes out of this, what can we do to increase power? All right, well, think about the area of this curve. Okay, one of the things that we could do, and the most popular thing we could do to increase power and thus reduce the probability of type 2 error the most popular thing is to increase the sample size, increase n. Okay, all right, what would happen there is that would decrease our variability and it would decrease the overlap because it would make the curve shoot up real high like that. So it'd be, as opposed to looking like this, they would go way up high like that and way up high like that, and there would be hardly any overlap. Okay, and so that would do that. The other thing you could do is you could increase alpha. Okay, think about increasing alpha. Alpha at 0.05 is that area there. If we increased it, that would move this line, our rejection region, to the left, and it would make the probability of type 2 error smaller. Okay, smaller. Okay, increasing alpha increases the percent of the time that you're rejecting everything, both good and bad. Okay, so there's a trade-off here. When you increase alpha, you're decreasing type 2 error, but you're increasing the probability of type 1 error. Okay, so there's a trade-off there. So increasing the sample size is very popular. The other thing you could do is you could change your hypotheses. Change your hypothesized value, your P naught. Like if you moved your P naught down to 10% down here, okay, and you in essence move these curves away from each other, there'd be less overlap, and so that would be less type 2 error and less power. So so that's it. That's your little thing for today. And this, now let me just say this about this problem. You know, doing a problem like this has only really occurred once on the exam, but the parts of this problem have occurred. And I think it's important really to understand, here's what is asked about a lot. It gets asked about a lot. What increases power? And that would be these three things, mainly increasing the sample size. The other thing they'll do is they will, like, let's say they give you the probability type 2 error and ask for the power. And that's an easy problem because you just subtract it from 1, or vice versa. It could give you the power and say, what's the probability of type 2 error? But that's it. So ask me a good question and maybe I'll give you one of my fun little otter erasers. Isn't that great? Okay. Thanks for stopping by. Hope you have a great day.